Intermolecular forces or van der Waals forces. The forces of attraction existing among the molecules of a substance called intermolecular forces or cohesive forces. These forces are of three different types as explained below. First type, dipole-dipole attraction. These forces of attraction occur among the polar molecules. The reason for the being origin of these forces is quite obvious. Polar molecules have permanent dipoles. The positive pole of one molecule is thus attracted by the negative pole of the other molecule. A simple example is that of HCl, in which chlorine, being more electronegative, acquires a slight negative charge, whereas the hydrogen end becomes slightly positively charged. The dipole-dipole attraction then takes place among the HCl molecule as shown in figure 2.2. Figure 2.2. Dipole-dipole attractions among HCl molecules. Proof for the existence of dipole-dipole forces. If dipole-dipole forces exist among the polar molecules, they should have higher melting point and boiling points than the non-polar molecules, provided all other factors like molecular mass, molecular shape, etc. are the same. This is actually found to be so far. Example, the non-polar molecules nitrogen and oxygen have boiling point 196 degrees Celsius and 183 degrees Celsius respectively, where NO, which is slightly polar, has a higher boiling point 151 degree. Magnitude of dipole-dipole forces. As the charges at the ends of polar molecule are not as great as the charge on the ions in an ionic compound, the magnitude of dipole-dipole forces is therefore much smaller in comparison to ion-ion attraction or ion-dipole attraction. Further, where the forces of attraction between two ions is inversely proportional to r square, the force of attraction between two dipole is inversely proportional to r is 2 power 7, where r is the distance between the ions in the former case and that between the dipoles in the later case. Consequently, under similar condition of temperature and pressure, since the intermolecular distances are very large, the dipole-dipole forces of attraction among the gaseous molecules are very small as the pressure is increased or the temperature is decreased. The distance among the molecule decreases. The molecules come closer. As a result, the intermolecular forces of attraction increase and the gas changes into a solid or liquid. The magnitude of dipole-dipole forces in different polar molecules can be predicted on the basis of the polarity of the molecules, which in turn depends upon the electronegativities of the atom present in the molecules and the geometry of the molecules. The polarity of the molecule are usually expressed in terms of dipole-dipole moment of molecules. For example, comparing the molecules of NH3 and H2O, the dipole moments are 1.49 and 1.85 dipole respectively. Thus, though both have nearly the same molecular mass, the intermolecular forces of attraction are stronger in case of H2O than those in NH3. Consequently, H2O has higher melting point and boiling point than those of NH3. In fact, it is well known that where H2O is liquid, NH3 is gas. Hydrogen bonding. It is special case of dipole-dipole attraction. It occurs in molecules containing a hydrogen atom linked by a covalent bond to a highly electronegative atom but small in size. Because of large electronegative difference between the hydrogen atom and the highly electronegative atom, the hydrogen atom acquires a significant partial positive charge and the electronegativity atom acquires a significant partial negative charge. The positive hydrogen end of one molecule that attracts the electronegative atom of the other molecule. For example, the cases of HF, H2 and NH3 may be represented as below. HF, H2O, NH3. Because of the greater polarity of these molecules, the intermolecular forces of attraction are stronger than the ordinary dipole-dipole attraction. That is why this type of intermolecular attraction is considered as a bond rather than mere dipole-dipole attraction. This type of bond is called hydrogen bond and is represented by dotted lines as shown in the examples given above. To sum up, hydrogen bond may be defined as the attraction of hydrogen atom of one molecule by the electronegativity atom of the other molecule in case of compounds containing hydrogen atom linked to highly electronegative atom small in size. Further has shown above in each case, the hydrogen atom is linked to two electronegative atoms simultaneously, one by covalent bond and the other by hydrogen bond. Thus, hydrogen acts as a bridge between the two electronegative atoms. This is sometimes referred as hydrogen strength of hydrogen bond. As mentioned above, hydrogen bond is stronger than ordinary dipole-dipole attraction. However, it is much weaker than the covalent bond. The energy of hydrogen bond lies between 20 to 40 kilojoule per mole, where that of the covalent bond is usually between 160 to 600 kilojoule per mole. Depending upon the electronegative atom, the strength of hydrogen bond follows the order. Dipole-induced dipole attraction. The positive end of a polar molecule may attract the electron cloud of a non-polar molecule lying close to it, thereby polarizing it. Thus, the non-polar molecules become an induced dipole, just as it happens in case an iron piece is brought close to a magnet. As a result, attraction takes place between the polar molecule and the non-polar molecule. Force of attraction between a permanent dipole and an induced dipole. Permanent dipole, induced dipole. 3. Induced dipole attraction, other name London forces or dispersive forces. It is easy to conceive ion-ion attraction, ion dipole attraction and dipole-dipole attraction. However, the next very significant question is what intermolecular forces attract non-polar molecules to each other in the liquid and the solid state. The origin of these forces was proposed by Fritz London in 1930 and they are termed as London forces. These forces are thought to arise from the motion of the electron. It is believed that at any instant of time the electron cloud of the molecule may be distorted so that a momentary dipole is produced in which one part of the molecule is slightly more negative than the rest. The momentary dipole induced dipole in the neighboring molecules. These are then attracted to each other exactly in the same way as the permanent dipole. The forces of attraction between the induced momentary dipoles are called London dispersion forces. It may be pointed out that since all molecules contain electrons, London forces also exist in the polar molecules. However, in case of non-polar molecules substance, London forces are the only intermolecular forces that exist. Magnitude of London forces. London forces are the weakest intermolecular forces. Their magnitude depends upon the following two factors: complexity of the molecules and geometry of the molecules. Complexity of the molecules. Larger or more complex are the molecule, greater is the magnitude of London forces. This is obviously due to the fact that the large electron cloud are easily distorted or polarized. Since the larger molecular size amounts to larger molecular mass, it is often suggested that the magnitude of London forces increases with increasing molecular mass. Geometry of the molecule. The shape of the molecule has a significant effect on the magnitude of London forces. For example, N-pentane and neopentane have the same molecular formula C5H12, yet the boiling point of N-pentane is about 27 degrees Celsius higher than that of neopentane. The difference can be attributed to the different shape of two molecules, the N-pentane being a zigzag chain, whereas neopentane is nearly spherical. N-pentane zigzag shape, neopentane spherical. The overall attraction between the molecule is greater in the case of N-pentane because there are more sites of interaction. The molecules are able to come in contact with the entire length of the molecule. Quite often, London forces are referred to as van der Waals forces. However, is it incorrect to call London forces alone as the van der Waals forces? In fact, van der Waals forces is generally term plays all types of intermolecular forces. Great contact between N-pentane molecules, less contact between neopentane molecule as shown in figure 2.5. It is interesting to mention here that based on the nature of intermolecular forces, the liquids are classified into the following type.